there is one aspect of the Fourier series I want to talk about, which is in relation to music. In the old days, like in the 60s, people were using electric synthesizers for music, but that was the time when we didn't have any personal computers. So the synthesizers were not digital, but it was analog. All the sounds were made by analog circuits. But analog circuits, they can't do anything fancy, so when you build these analog synthesizers, they would have waveforms that look like this. So there's something called like a saw wave. And then sometimes you might have a, like this, that's a square wave. And these were the two most widely used ones, and somewhat uninteresting is the sine wave. And then you also had the triangular wave, which sounded a lot like the square wave. I guess there's some small differences. So you have this. And so there will be some wave generator that will generate these basic waveforms and send it to some filter. Like these sounds are rather harsh. I did bring my keyboard, but this one has a lot of effects added. So to let you hear the pure square wave, here's a pure square wave. Okay, doesn't sound too nice, right? But if you put some reverb, let me see where I have that. There. Okay. So that's what happens if you put some additional reverb. Just like that, right? Sounds more familiar, right? Okay, yeah. Right, yeah. Much better than this. Okay. And then there is the saw wave. Let me show you the saw wave. Do you see the difference? Can you hear the difference between a saw wave and a square wave? This is a saw wave. Okay, let me play a saw wave. What happens if you put some reverb and other effects? That's again. So if you want to compare the square and saw, it's like square is it's kind of dreamy and more bright, right? Whereas saw wave is just like that, right? Okay. So if you were wondering why I brought my keyboard, that was it. Okay, there's nothing.
You gotta play a song at the end of class for us, though.
No, I don't know any song. All right.
Yeah, that was a pretty good song.
Okay. Yeah, except that for a complete square song, right? Okay. Back to work. Okay. So what I want to do now is actually talk about the Fourier series of the saw wave and the square wave, and then I might just say a little bit more about this one, but not much about the triangle. Okay. So. What's a Fourier series of a saw wave? Well, you have to take a Fourier series of one period. So you see that this is repeated, right? This is like one thing that's increasing and then suddenly drops down, and then this is really not part of the function. It's like that and then drops down. So it's a function with jump discontinuity. but I should do this one. Yeah. So it's just this red part, that's one period, right? That's just being repeated over and over. Now what's a good function that would behave like that? Well, if you just have the window from negative pi to pi of this straight line, I know a function that does that, which is y equals to x, right? So just finding the Fourier series of this function y equals to x will give you a good idea of what the Fourier series of this will look like in general. So let's try that on. Now, because this is an odd function, when you represent the function as sum of a0 over 2 plus sigma an cosine nx plus bn sine nx. See, this is an even function. Constants are even functions, so they are not going to show up at all. If you calculate a0 and if you calculate an, you'll see that they're both 0. Okay? You can kind of see why, right? If you multiply x times cosine, x is an odd function, cosine is an even function. So if you multiply, you get an odd function. And if you integrate from negative pi to pi, you're going to get 0. Okay? So you're not going to see any of these. So the only thing that you have to compute is bn. And that makes our life really easy, because instead of having to calculate 3 of them, you just have to calculate bn. So let's calculate bn. bn is 1 over pi integrate negative pi to pi of the function x times sine nx dx. And then when you integrate this using the tabular, plus minus the integral x1 0 sine nx integrates to negative 1 over n cosine nx integrates to negative 1 over n squared sine nx plus minus plus. And when you multiply, you get negative x over n cosine nx plus 1 over n squared sine nx. And plug in pi and 0. Oh, I forgot to do that trick, 2 over pi, because x is odd, sine is odd, product becomes an even function, so you make it as 2 over pi, but your integration is not from negative pi to pi, but 0 to pi. And again, you see that when you plug in pi, this will be negative 1 to the nth power, this will be 0. When you plug in 0, nothing shows up. So your final answer will be just 2 over pi times negative pi over n, negative 1 to the nth power. Canceling this, you just get negative 2 over n, negative 1 to the nth power. And that means that your function f of x can now be represented as summation of n equals to 1 through infinity of negative 2 over n, negative 1 to the nth power of sine nx. Okay. So that's one result. I'll talk about what that means after we do the square wave. Now, what about the square wave? Well, again, these are functions with jump discontinuities, just like that. And I claim that this function right here would be this much right here in red is one period, right? Because everything else after this is just a repeat of this, right? You have this and then repeats. Okay. Control C, Control V, Control C, Control V, Control V, Control V. It's a periodic function. And then you have to model this, and I claim that a nice function that would do that is like you have a function which is 1 from 0 to pi, and let's just make it open circle in between, but then negative 1 from negative pi to 0. So that's like that portion. Okay? And if you repeated this many times, you're going to see a square wave, right? And if you are curious to know how to represent this as a function, well, you will have to use it as a piecewise function. So f of x will be 1 when x is positive, -1 when x is negative. Now, question. Is this an even function, odd function, or neither?
Yeah.
It's odd because you have one side going up, the other side going down, right? Now, being odd means it's symmetric over the origin, and you check, you take a you reflect over the origin by doing reflect over the y-axis, and then you flip upside down. You do the two things, you get the reflection over the origin. And indeed, if you take this picture and you flip this side, and then you flip this side, you end up with the same picture. Can you imagine that? So this is indeed an odd function. Now, again, because it's an odd function, from the same logic, you're not going to see a0 and an. We only have to do bn. Good? And furthermore, we can just say bn is 2 over pi, integration from 0 to pi, of f of x sine nx. But wait, since fx is being evaluated only for 0 to pi, what is f of x? From 0 to pi, what is f?
1.
1. So even this is not needed. And that's just an integration anybody can do. It's just 2 over pi times 1 over n, actually minus 1 over n, cosine nx. You have to plug in pi and 0. Now this time, even if you plug in 0, because there's no x multiplied, it's going to be giving you 1. So you do get values for both. And the result is that you have -2 over n pi. When you plug in pi, you get -1 to the nth power. But when you plug in 0, you get 1, so you subtract the 2. So that's what you get. And therefore, finally, the answer for this case, the square wave, will be summation of n equals to 1 through infinity of -2 over n pi, -1 to the nth power minus 1, sine nx. Okay. So these are the two functions Fourier series. Okay. Now from this, the first thing that we realize is that these complex waveforms are really sums of simpler sinusoidal curves, right? Actually, that's what the Fourier series is saying. You have any complex waveform, you can always represent them as sum of sinusoidal curves. Okay? So this one and this one are actually a bunch of sums of this, but with different frequencies. Okay? Now, if you are interested in how sine wave sounds like, sine wave is rather dull. Let's see, where is the sine wave? Here. Oh, after some effects, it sounds much better, but it's very simple. It's smooth, and it's just one frequency that it resides. So, in fact, in the 80s, Yamaha came up with a revolutionary synthesizer called DX7. And DX7 could only produce sine waves, but it could produce 6 sine waves. Now, what do you do with these 6 sine waves? You can add them, you can multiply them, you can also put one into another function. You can compose 2 sine functions to make something really more complicated. But in that DX7, there were many sounds, and one of the sounds was saw wave. Even if it only could produce sine waves, it was able to produce a saw wave. How? This. It would just add a bunch of sine functions with different amplitudes to come up with a convincing saw wave? Well, the thing is, you only have 6 of them, so it doesn't have the higher frequency, so it's lacking somewhat. So people didn't really like it, but still, it was something like a saw wave. The square waves were also produced by using this. They would be able to produce something similar to this by adding a bunch of sine waves. Okay. So this did get used in music. There is something else that I want to talk about that's a bit strange. If you look at these values, here, for any n, it's always some value, right? But what happens to this one when n is even? What happens to this one when n is even?
0.
That becomes 0, because negative 1 to the even part is 1. 1 minus 1 is 0, right? So here's what happens. The saw wave, if you drew the frequency graph against the amplitude, now because we're talking about amplitude, even if you have a negative number in front of sine, we'll just put a positive number there, right? Now look at what the amplitude is doing. It has 1 over n. It decreases like 1 over n, right? So what it means is that when angular frequency is 1, you get certain value. Angular frequency is 2, you get another value. You get another value, but it's decreasing like 1 over n. So this is called the graph in the frequency domain. When you think about the function as sum of bunch of different frequencies, we see that the saw wave is made up of these sounds, something like this. They add like that, okay? On the other hand, this one, every time n is even, if the angular frequency is even, it's going to be missing. So the even part will be missing. Okay? And that's the difference in the sound you hear. See, our brains are really good at processing frequencies. So when you hear the saw wave, you kind of feel that all the frequencies are covered. There's something in every frequency. However, when you listen to the square wave, there's something that's missing. Now that kind of explains why for analog synthesizers, saw waves were more preferred than the square waves, although this had its nice properties. Like, it sounded nice to some people, but this was more preferred because this had every frequency, and therefore if you want to manipulate the graphs, like there's some see, if you have a saw wave and if you apply a resonant filter kind of like takes a few frequencies and boosts them up to sound like sharper. So you can use that, or low pass or high pass. High pass will make the sound thinner. All kinds of filters can be added to the saw wave, and because it had every component, it would better behave. You would be able to shape the sounds better. So more people were using the saw wave, and nowadays, like in any techno music or EDM you listen to, you will hear that saw wave in some form. Like any kind of synth that you hear, it's really the saw wave in some different form. Okay. Now you probably have seen in physics, you learned about standing waves, right? So you have standing waves. If you have an open pipe, then you had something like this as one of the standing waves. But if you have a closed pipe, if a pipe was closed on one end, then a standing wave would look like something like this, right? Yeah. And the result was that, I can't remember which is which, but one of them were missing some of the components, some of the frequencies, when you compare the other. And in church organ pipes, they have both kinds of pipes, and they sound different. It's almost the same situation as the saw wave and the square wave. So I found this interesting. So to close this, all I'm trying to say is that what does the Fourier transform do, or Fourier series do? It changes a usual function into a frequency domain. It allows you to see what the function looks like in the frequency domain. And by doing that, you can learn more, especially when it comes to sounds. This gives you more insight than just seeing the waveform. If you just see the waveform, you wouldn't be able to think about the sound. But if you look at the frequency domain, then you have a better idea. Not that you'll be able to see the sound, but you have a better idea of how the sound will be like. Okay. All right, that's everything for today.